Here are the notes for Unit 3.5, Uniform Electric Fields and Electric Potential Energy. So we're going to start off by focusing on uniform electric fields. The word uniform means it's the same everywhere. And here I've got an example of a uniform electric field. And I want you to think about what kind of charge could create this field. So if we had two charged plates, and if one plate was positively charged and one plate was negatively charged, then our electric field lines would point away from the positive and toward the negative. If I were to draw a positive test charge, and see if I can animate this a little bit, and then if I were to take that positive test charge, it would move away from the positive and toward the negative. Now, this is really similar to gravity, but I have this turned on its side. So I'm going to try this again. I'm going to snip this. And I'm going to copy it. And I'll paste, I'll paste it. And I'm going to rotate it so that it's more like a gravitational situation. I want to think about this as having a ceiling and a floor. If you're in a room with a ceiling and a floor, then we've got the ceiling is at high potential. And at the ceiling, an object with mass would have high potential energy. And at the floor, we have low potential. And as the object falls, it gains kinetic energy and loses potential energy. And that's the same thing with a charge between two charged plates as a mass between a ceiling and a floor. The charge, as it travels from high potential to low potential, is going to lose potential energy and is going to gain kinetic energy. Let's take a look then. In our last unit, we were looking at point charges, and here I've got a simulation. I'm going to turn on the grid here. If I put a single charge in this field, this is a vector field, and the arrows show the direction of the electric charge. The direction of the electric field created by this positive charge. I can remove that, and if I put a negative charge, I would have a similar shaped field, but the direction is opposite. If I have two charges, I get a field that looks like that, and we've seen how that looks before. And now what I want to do is I want to simulate that ceiling that I had before. So I'm going to take these charges and place them on this grid. I'm going to take some negative charges and do the same. And so with many point charges, we can create a uniform field. So in the center, we can see how in the center the arrows are pointing straight down. And again, we've got that uniform field in the center. And on the edges, we get a curve. So let me switch back to my notes. So my field is down and straight in the center, and it's curved on the sides like that. And that's a uniform electric field. Okay, so as a charge moves through the field, there's a change in potential energy as long as the charge moves parallel to the field. So let's say this is my charge. So if I move the charge up and down, I'm going to change the potential energy of the charge. The charge has more potential energy if it's being held toward the positive charges, less potential energy as it moves toward the negative charges. If I move it horizontally, the potential energy of the charge does not change at all. It's kind of like height for gravitational potential energy. When I move it back and forth, the height here is remaining the same. So the change in potential energy would be equal to the work done on the charge to move it in that field. Now, in an electric field, we've got that force equals Q times the electric field because the electric field is defined as F over Q. And we can substitute to say that the work done is equal to negative QED. The negative sign indicates that the electrical potential energy will increase only if the charge is negative and decrease if the charge is positive. And this equation works only in a uniform electric field. So just to sum up, if I take a mass and I lift it a certain height, I'm going to give that mass gravitational potential energy. Let's do delta H. And that gravitational potential energy is going to be equal to the mass times G, which is the strength of the field, so that's supposed to say field strength, and delta H is the displacement. The direction matters, right? Because up is going to increase the potential energy and down is going to decrease the potential energy. If I'm dealing with a charge, let's say I've got a positive charge and I lift it up, then Q is positive. In this scenario, E is actually negative because it's pointing down. The electric field is pointing down, and the distance is positive. But in this scenario, the potential energy, actually I should use a U, the electric potential energy is increasing if I am to lift this charge up. And that means that it's a positive value. And so in order to get a positive value when I plug in these numbers, I need that negative in the formula. Okay, so let's try an example. Find the electric potential energy stored by moving an electron from the low potential plate to the high potential plate if E is 30 newtons per coulomb and D is 20 centimeters. So in this scenario, a couple of things to note. First of all, the positive plate is always the plate of high potential, and the negative plate is always defined as the plate of low potential. That's just a definition. Okay, next, I'm going to write down what I know. I know Q is negative 1.6 times 10 to the negative 19th. I'm going to switch colors here so it's a little easier to see what I'm doing. E is negative 30 newtons per coulomb. Now, E is a vector, and it's pointing downward. In this picture, the direction is given by the diagram. So again, I know that this is a negative value because of the diagram, even though it doesn't say negative in the question. And then D, the distance, is 0.2 meters, 20 centimeters. And it's moving from low to high potential. So up is positive. So again, I'm designating up as positive and down as negative. So I'm simply going to plug those numbers into the formula. Electric potential energy is negative QED. And then I'll solve, and I get 9.6 times 10 to the negative 19th joules. Let's try another one. And this is a similar problem, but notice instead of electricity, we're dealing with gravity. Find the gravitational potential energy stored by moving a 1 kilogram mass from the low potential floor to the high potential ceiling if G is 10 newtons per kilogram and D is 3 meters. So I want you, again, to notice the similarities here. Gravitational potential energy is based on mass, field strength, which is G, and H, which is height. And that's very similar to what we have up here, except we have Q, electric field strength, and D. So I plug in the values that I have, and I get that the gravitational potential energy is 30 joules. Okay, let's try something a little different. What would happen if the electron in example 1 were sent perpendicular to the field at 1,000 meters per second? Now there's a simulation that you can try for this. Let's see if I've got myself set up. Oops. A milk and oil drop. This is a simulation created in GeoGebra, which is pretty cool. And so what I'm going to do is this charged particle on the left is going to travel. When it gets into the field, it accelerates. Okay, and this is the same. This is the same as a horizontal projectile. The weird thing is that because of the way electricity works, because we have both attraction and repulsion in electricity, the object is actually accelerating up. Normally, when we deal with horizontal projectiles, we have things accelerating down. So that's kind of interesting. So let's go back to our problem here. So let's see. So I can figure out, based on the electric field, and I can figure out the force on this electron. And then based on the force on the electron and the mass of an electron, which is a given, I can solve for that acceleration of the electron. So again, the electron has a horizontal velocity, and then it also has an acceleration in the vertical direction. Just to note that I could figure out a bunch of things with this. I do know that horizontal range or position is equal to Vx times delta t. And then in the vertical position, I know that delta y equals 1/2 a delta t squared. Those two equations apply to this situation just like they do to horizontal projectiles. One more example for today, example 4. A pith ball with mass m is suspended in a uniform electric field E. It hangs at an angle theta. Determine the charge on the ball in terms of m, e, theta, and the fundamental constants. Okay, so you can see here we've got these charged plates. So the electric field is to the right, and that tells me that this must be a positively charged object being pushed to the right. And you can see that the electric force is to the right. We also have a tension force and a force of gravity. Now, these forces sum to 0, which means that the electric force balances out Ftx, or the horizontal component of the tension, and the gravitational force balances out Fty. So I can use trigonometry, opposite and adjacent, to write the formula for the tangent. The tangent of the angle is the opposite side, which is Fe, the same as Fe, over the adjacent side, which is the same as Fg. And then I can plug in the formula for Fe and the formula for Fg, which is what I've done over here. And then I solved it for Q, and I got that Q equals mg tangent theta over E. All right, good stuff. Okay, one more idea here. Let's think about electric potential energy stored with 2 point charges. I want you to imagine for a minute that you have 2 positively charged objects and you try to push them toward each other, kind of like the sticky tape experiment. When you do that, there's going to be a force, a repulsive force, and you can store energy by pushing those two charged objects together and holding them together. You can store energy that way. The formula for the energy stored is this: PE electric, or U electric would be better, equals K times Q1 times Q2 over R. I've got 2 examples here. Here's one. In the classical model, an electron has a radius of 2.82 times 10 to the negative 15th meters. So 2 electrons could be as close as 2R. Calculate the electric potential energy for the 2 electrons that are quote-unquote touching. So here I've drawn a picture of 2 electrons right next to each other, and you can see the centers of them and their radii, and the distance between the centers is 2R. So to calculate the electric potential energy, I'm going to use the formula, plug in K, the charge on an electron, which is 1.6 times 10 to the negative 19th, and square it, because there's 2 of them. And then the distance is going to be twice the radius of an electron. And when I solve that, I get 4.1 times 10 to the negative 14th joules. Let's try one more example. What is the change in the electric potential energy of a proton as it moves a distance of 2 centimeters in the direction of a uniform electric field with a strength of 400 newtons per coulomb? When I solve a problem like this, I like to draw it. So I draw an electric field, a uniform electric field. And I know that a uniform electric field is created by 2 charged plates. So I've got a positively charged plate and I've got a negatively charged plate. And then the proton is moving in the direction of the electric field. I know they give me the magnitude of the electric field. It's a proton, so I know the charge on it, and I know the distance. So I simply plug those in and solve for the energy stored by doing that. By the way, if the proton moves to the right, then I know that the proton is losing that electric potential energy. All right, those are your notes on electric potential energy, and I will